first of all, Ramzan Mubarak to everyone. And as you know that timing has been reduced by 20%. So this lecture will be of about 60 minutes. That is why I was not informed early. I didn't got the mail. Then first of all, I was informed by CRFD section that timings have changed. Then I was then informed also by the chairman, Umar Shahid, that timings have been shifted as well as the lecture duration has been reduced by 20%. So we will be doing these lectures of about 60 minutes. Uh, so we will start with today's lecture. Bismillahirrahmanirrahim. Already in the last lecture, if you could remember, we had seen the second type of amplitude modulation technique, and that was conventional amplitude modulation. And this amplitude modulation is used especially for broadcast stations, especially radio broadcast stations. And we saw the main characteristics that you have a very high power carrier. This AC is also with 1. It also goes with MT, but it is we design our signals in such a way so that this value of MT is much smaller as compared to 1. And we saw how could it be done. First thing that was that you could normalize the signal by its maxima. Hence you will get a normalized signal which will be between 1 and -1, and then to further decrease this signal so that its magnitude is less than mod 1, we multiply this with the modulation index or the scale factor, which is also less than 1. So this means that this signal AMNT or this MT will be definitely for the whole time. This will be less than 1. All right, it's maybe it is positive or negative, but will be always, its mod will be always less than 1, or its positive or negative value will be greater than +1, or you can say in other words greater than -1, or in between +1 and -1. Hence this factor will always be positive, and if it is not positive, then we say it is over modulated. But if it remains positive, that means that then the signal is not over modulated. And we will be seeing in a while that this will help us in demodulating the signal. And we saw the spectrum is as before, but you have a very high power carrier which has actually a very high magnitude as compared to the magnitude of the double sideband signal. So you have the double side signal remains the same, but in addition to that you have this carrier AC cos, which is added. You could see in the previous technique, which was double sideband suppressed carrier, you didn't have a high power carrier, but we saw one technique so that we could add a pilot signal with the DSB signal, so that it could help us in coherent demodulation, so that you could get rid of that phi, because that there was synchronization problems between the receiver and the transmitted signal. But again, that pilot signal had a very small magnitude as compared to the magnitude of the DSB. But here in conventional, it is totally opposite. You can very well see that this power of 1 will be much greater than this power of combine this thing. So we also did this example, and we saw its spectrum. And we also calculated the powers, how to calculate these powers, and we again saw that the power in the carrier was much greater than the power in the combined two sidebands. So we will start from this point. Power of the conventional AM signal or you can see the double sideband with a very high power carrier. Now we know it is equal to a double sideband and the double sideband suppressed carrier, as we have studied before, it was just empty times cos, or empty times the carrier. Now what has changed? All the things are same, AC is the same, cos is the same, only the message signal has been changed to, instead of empty, it has actually become 1 plus, he has written MNT, but it is proper that we should write it as MT has been separated by 1 plus AMNT. There is a mistake here. This should be AMNT. So you could very well see in the equation here too, as I was telling you, this is now the equation. What was the previous DSB suppressed carrier? That was just AC MT cos 2 pi FCT. Now what has happened? Instead of that MT, you have 1 plus AMNT. That is the only change that has happened. So we can say that MT has been substituted by 1 plus AMNT. Alright. Now we have seen what is the power of a DSB SC signal in the previous equation, and it came out to be AC square over 2 PM, where PM was the power of MT. Now what will be the power of conventional? It will be the same, but instead of PM, it will be actually PM with respect to this signal. There it was PM for MT, now it will be PM for 1 plus AMNT. That is the only change. Alright, I hope you have understood. You can see the also previous proof. All the proof is the same. You just need to change PM to being power of MT, now change to being the power of the signal 1 plus MNT, 1 plus AMNT. Right. So PU is this. So what is PM now? For conventional, it will be the power of PM. And the power of PM is the power of 1 plus AMNT. So we know the formula 1 over T. This is T goes to infinity. And the signal is 1 plus AMNT. There's a mistake here. The 1 plus AMNT square. Signal square gives you power. When you integrate, this gives energy. And energy divided by time, this gives average power. Now I open this square. So it will become 1 square plus A square plus B square plus 2AB or 2AMNT. Alright. But you can very well see that most of the signals have an average value of 0. So the factor which will be the factor which will be 2AMNT will have MNT, and MNT, when it will be averaged, not its square but its simple value, when it will be average over t time t slot, it will come out to be 0, because the signal normally with B spoke have an average value of 0. So you are actually taking MT integrated over the whole time divided by time. So this is the average value, and this will come out to be 0. So we don't take that 2AB factor will go out, only this will remain. So this one, this will become T. Alright, small t, and when integrated T over 2 minus T, this becomes T. T cancels, this becomes 1. This comes out to be 1. This A square will come out of the brackets, and this when it will go on inside, this will be Mn squared T. This will be power of Mn signal. This will be written as PMN, or power of the normalized signal. So I will now put this value of PM in this equation. Alright, 1 plus A square PMN here. So this will now give me the total power of the conventional double sideband signal. This is the spectrum of the previous example that we did in the last lecture. There you can see the power of these carriers are actually greater as compared to the powers of the combined upper and lower sideband of the signal. So you can see the total power is now given as this, and now you can also see here that this AC square over 2 is common, but here A is less than 1, this will be a smaller number. PMN is also a normalized signal, and most of the time you have a very large dynamic range of the signal, which means that you have very low values of signal as well as you have very high values of signal. So when you will normalize it, you can very well see that the power will be quite decreased because you have divided it by the maximum value or by a very high value. So overall this factor will be much smaller as compared to this factor, or the power in the carrier is greater than compared to the total power of the sidebands, as you also saw in the last example. Second component, as I've told you, it carries the information, and the second component is usually much smaller because of this A. And then we also know that normalized signal is less than 1 for most of its time, and then if it has a large dynamic range, we know its power will be much smaller than 1. So we know that conventional AM systems are far less efficient, power efficient, as compared to double sideband SC, because they didn't have a carrier, and this has a very large carrier. But what is the advantage? Advantage is that we will be seeing in a while that you will be able to detect the signal very easily by using cheaper radio sets, and that is the main objective. So you apply high power at the transmitter, but all the receivers can have a very simple, all the receivers, all the listeners can employ very cheap receivers to get back your signal. So we have a signal M of t, it is given as follows, and so we have a carrier this cos 2 to the power 5. So modulation index is given as 0.85. So we want to find the power in the carrier component and the power in the sideband components of the modulated signal. So when it is given that modulation index is 0.85, this means we are doing conventional. And now first of all we have this signal. Okay, so first of all we need to normalize this signal. For normalization we need to find its maxima, then divide this signal by its maxima. So what is the procedure for finding the maxima? I will take its derivative and set it equal to 0. So its derivative, you can very well see this cos will become minus sign, and this 200 pi will come outside, this becomes minus 600, and here 600 pi will come outside, sign becomes a cos, and I put this derivative equal to 0. So this means that cos pi sine will be equal to 600 pi cos 600 pi t, and you can this 600 cancel, so you will finally have cos 600 is equal to sine 200 pi t. Then sine can always be written as pi by 2 minus cos alpha, because when you will open this with the some angle formula of cosine, so you will have cos pi by 2, which will be 0, and then you will have cos 200, but 0, this first factor cos alpha beta will cancel, minus will become plus, sine pi by 2 is plus 1, and sine 200 pi t will come here. Alright, so this can be written with the help of the cosine a plus b alpha plus beta formula. This is cos, so the arguments must be same, so we can write 600 pi t is equal to pi by 2 minus 200 pi t, so minus 200 goes here, this becomes 800 pi t is equal to pi by 2, and hence t comes out to be 1 over 1600. So at this value of t we will have the maxima, so I will put this value of t 1 over 1600 in this equation. T will be replaced by 1 over 1600, and I will calculate my mt. So mt comes out to be this value 3.6, 3.7 approximately, which is the maximum value. So I will divide my complete signal by the maximum value, and I will get my normalized signal, which always remains less than 1. So this was your original signal, and this will be normalized to give you this signal. Now, what is the power in my normalized signal? Because you know that power is needed to find the total power. So you know we will use the famous Fourier series formula. So you can see you have one cosine and one sine, and we all know cosine is 2 ej's and sine is, you know, it is ej minus ej over 2j. And so we have 4 exponentials, and you know this is a periodic signal, so we can very well use the Fourier series formula for finding the total power, and we can see that formula. We have also studied this in the last lectures. So it shows us that the power in this is just equal to the mod or the square of the Fourier series coefficients. So Fourier series coefficients for, you know, ej will be this thing over 2. All right, and this will also be square over 2. Now this value over 2, then you will take its square. This will become 0.8 square over 4. The other factor, other ej will also be the same thing. The total power will be 0.8 square over 4 plus 0.8 square over 4. So this will become 0.8 square over 2, and this will also become 0.27 square over 2. All right, because you have 2 exponentials, that is why. So you will just do it like this, and you will get the total normalized power. So again, you should know that we have used the famous Fourier series expansion for powers. So, and by the help of that, we can get the total power. आनी सबको समझ आ गया how we have found the power of this sum of two sinusoids? Is everyone clear? हाँ जी सलमान जमील साहब समझ आ गया?
सर एक चीज है इसमें सर, ये
सर क्लियर। अच्छा हाँ जी, someone has any question? Good. फैजान अरशद साहब, yes you can ask.
सर ये जो आपने 8 पाई टी है वो जरा रिपीट कर दीजिए, कैसे आया था?
अच्छा हाँ ऑलराइट. We can write sine 200 pi t as cos alpha minus beta. All right. So both are cos. This means 600 pi t will be equal to pi by 2 minus 200 pi t. All right. So this means 200 you can take it here. This will become 800 pi t will be equal to pi by 2. This is what is 800 pi t is equal to pi by 2. Pi cancels, so t comes out to be 1 over 1600. We will put this value 1600 in the m equation, in this m of t. So at this time you have the maxima. Just put this value in the equation, you will get the maximum. This you can also see, this is the maxima of the signal. Alright? हाँ जी फिजान साहब समझ आ गया?
जी सर आ गई समझ सर.
अच्छा. So now we have found the normalized power. So now we can find the total power. So what is the power in the carrier? You know, power carrier is always AC square over 2. Alright, and in this question he has taken AC to be, so there is 1, AC is 1, this will be, you know, 1 square over 2. And the power in the sidebands, you know, is for AC square, A square, PMN has been found, A square is already given, A is half, and you will get this power. So you can see power in the sideband is 0.13 and power in the carrier is 0.5. So you can see the order difference, that the power in the carrier is much greater or more than double as compared to the total power in the sidebands. Now we have seen that why we are doing this. So I told you the basic philosophy was to make cheaper radio sets. So how it becomes cheaper, let us see that. So it is written here, E's in the signal can be demodulated, and the best thing is that you do not need a synchronous demodulator. If you could remember in double sideband suppressed carrier, what was happening? You needed to multiply the signal by a cos. If you have sent the signal by a carrier, you needed the receiver to have the same carrier. So you know how to make a carrier. Let us say my carrier is going at 100. Let us say if it is FM 100. So I need a 100 megahertz signal inside my radio set. For that, I will need to have an oscillator. And you know, as frequencies increase, your oscillators, they cannot be made by simple RLC circuits, and you have to go to electromagnetics to make these, you know, very high frequency circuits work in gigahertz or higher megahertz. And for optical, you have to go to optical circuits, so they become expensive. All right, so and that is why your receiver become expensive to have this synchronous मतलब के demodulators, where you have synchronized, you know, costs, because you know, if you have a cost coming, then you multiply with the cost, and you also need to have synchronization so that there is no phase difference between them. For that, you know, we have other procedures to do that. You might apply a phase lock loop, or you might apply a pilot, but again, you know, everything has a cost. Phase lock loop, you will be standing, it needs another, you know, phase lock loop circuit, and for a pilot you have to divide the power, as well as you need, you know, the same oscillator and all that expensive items in your receiver. So conventional does not require all this synchronous circuits or synchronous demodulator receivers. And why this is possible? Because we have made sure that this MT is less than 1. And now this MT means, you know, AMNT, or all the normalization. Or you can just say, if my signal, I am 100% sure that my signal MT is less than 1, then you do not need to do normalization, and you do not need to do scaling if you already know that MT is less than 1. All right, because once it is less than 1, then you know 1 plus MT will always be greater than 0, because you know 1 is a DC signal, and MT, if it is less than 1, then you know, in terms of magnitude, then you know 1 will never go to 0, so your signal will always be above 0. And so if you rectify the signal, what will happen? You will just get the positive cycles, or you will get the total envelope of the signal, which is actually the message signal but having high frequency parts. And so you rectify the signal, and then, you know, rectify, you get the positive part still, but you have a high frequency part, but you pass it through a low pass filter, okay, with the bandwidth as equal to the bandwidth of the message signal. And then this combination of this rectifier and low pass is called the envelope detector, and you will get the output from the envelope detector. Envelope detector in general has a DC output and the original signal, so you can always get rid of this DC output by passing the output to a capacitor. You know, capacitors block the DC part, or you can put this to a transformer. Again, you know, transformer, they will not pass the DC signal to their secondary, because you all know from now electromagnetics very well that you need change of flux linkages and all that for uh, you know, for induced EMF and all that. Okay, so you can get your G2 empty by a capacitor or by a transformer. This is a functional, which is just, you know, here for your concept building, but details will come in the subsequent lectures. So you can see this was my high frequency carrier. All right, and this was the output that I was getting after the signal has been passed through a rectifier. All right, so if now I apply my low pass, so I will be getting this output, this black lines. We will be seeing how we will get this once we go to the circuit part, and this will be called the envelope. The envelope is actually the message signal which is riding on top of your high frequency carrier. So simplicity, just you need a rectifier combined with a low pass filter has made this a practical choice for AM radio broadcasts. So you have billions of radio receivers having inexpensive implementation of demodulator, and so it is inefficient. But what's the deal? If the receivers, if everyone is tuning to your radio, then this is what you required. And Yeah, you have few broadcast transmitter, large number of receivers, so you sacrifice power efficiency so that you have higher, market penetration, and more users are keen to listen to you because of the inexpensive cost of the receivers. So in market, this is always a play of how much you spend so that how much you can get. So the next part is the single sideband amplitude modulation, or the third type of amplitude modulation is single sideband. Now, why we need single sideband? Both previous were double sideband, suppressed carrier or double sideband conventionally, okay? But they were all double sideband, and we know in double sideband we have double information, but we actually just need a single sideband which will have all the information. So required bandwidth we know is 2W, where W was the actual bandwidth of the exact message signal was only W. So we know that these two sidebands, one of the sidebands is redundant. Even if we get rid of that, we can still get back the whole information from the single remaining sideband. Yes, either sideband is sufficient to reconstruct the signal. And then what is the advantage? If we are able to just send a single sideband, not a double sideband, then we will just require W bandwidth. We won't require 2W bandwidth. All right. So this is a picture which is I am not able to show it properly, but still you can just gauge. This was your double sideband, this and this. This was upper sideband, this was upper sideband. This was lower sideband, this was lower sideband. Now, for example, if I just take the upper sideband, so I do not need this part and this part. I am just sending this half of this signal, and here I am also sending only this half of this total signal. So advantage is that I will just be requiring this much bandwidth. And when this actual signal was in the base band, the bandwidth was W. For double sideband, it became 2W, but now I still require only W if I just send a single sideband. W in positive and W in negative. So we, always count positive. So industrially speaking, you just require W bandwidth. So any industrialist who is investing his money, he will say, oh, now instead of putting 100 users, previously let us say I was putting 100 users in my double sideband signal circuit, now I can put 200 users. So I can give my mobile services, or let us say 99 services, to double the users. So why not use single sideband? All right, I hope you've understood. If you have not understood the figure, there might be some figure here which I could. So yes, this is also we can use this. So what we are doing, we will be not sending this part and this part. We will just send this part and this part. All right. So we are sending the upper sideband. Vice versa, I cannot set the upper part, upper sideband. I just send the lower and the lower. I will be again sending only the lower sideband. And you can see the bandwidths I will be sending will be only W, not 2W as previously. So bandwidths are very, very expensive. All right. So in that way, you can save a lot of bandwidth, a lot of expense, or you can double your profits. All right. So we will be seeing in the appendix that this single sideband signal can be mathematically written as follows. So don't worry, I will be going this in detail through my notes now. Achha. But before we go, just as general description, let us assume that this is a signal of a single sideband. If this is negative, this will give you upper sideband. If this is positive, this will give you lower sideband. This hat of T, hat of M, this is called the Hilbert transform. We will be studying this also today. And all that. This Hilbert transform, you can see, you can assume as if its impulse response is 1 over pi t. We will be also seeing this in detail, why this is 1 over pi t. And the frequency response is given as follows. That is for positive frequencies, it introduces a delay, phase delay of minus j. All right, because this is phase. And for negative frequencies, it produces its frequency response is J in imaginary, and which we know it only affects the phasor component, not the magnitude, because magnitude doesn't change. We will be seeing this in detail now. Now, with all that, let us just try to go to the big picture, the system view. So this is my signal. You need to generate the signal as follows, even the upper or the lower sideband. So I can just write my system diagram as signal is coming. I take its Hilbert transform. I get my m hat of t. I multiply mt by a cos. I shift my cos by 90. I get sine. I multiply my m hat by sine, and then I add them. If I am adding them, I will get the lower sideband. If I am subtracting them, I will get the upper sideband of my single sideband AM signal. There is another way also, and that is that you just do your simple DSB suppressed carrier modulation, but then you pass it to a band pass filter, which just passes the upper sideband or the lower sideband. All right, it cannot pass. It will just pass the upper. So by this help of this filter, you will again get the upper sideband or the lower sideband double side okay, single sideband signal. All right, so this is also a way, but remember here that band pass filters having these sharp cutoffs is not that possible, and if you want to make these very sharp filters, then you have to go to electromagnetics. You have to go to very high frequency, or you have to apply detailed electromagnetics analysis. And again, this is a huge field of filter theory. So we are actually, you might be getting an email in pass in the recent coming weeks about a PhD thesis which has been submitted by uh, one of foremost engineers of Pakistan working in satellite industry uh, for doctoral thesis in UET. So there you will also get an idea how can you make these sharp filters with the help of electromagnetics and filter theory as well as circuit analysis for industrial purposes, especially for satellites, because in satellites you have a very high constraint. You have a huge number of users, applications, very large bandwidth, and the filters are very expensive. They have to be sent in outer space and all that, and it is and they are designed. Uh, those students are interested, you will be getting an email from the postgraduate research center. So those who are interested, they can very well see those designs. So bandpass filters having sharp cutoffs are difficult, especially when you are designing with simple RLC circuits. Even for electromagnetics, it is not that easy, but there is a huge industry, huge research behind them, and the engineers are making sharper and sharper filters by research with every coming day. All right, let us go further. So this was a general description, but the mathematics was left. So first we will try to do the relevant mathematics. So first of all, we go to chapter 2. One part that I left in chapter 2 was this Hilbert transform. So first let us try to understand a little bit about Hilbert transform. Alright, Hilbert transform and its properties. So it is a transform, it transforms the signal, but is unlike other transforms of electrical engineering. For example, Fourier transform, Laplace transform, and Z transform, which were actually transforming a signal from time to frequency, or vice versa, or time to S domain, and then you can also go from S to frequency, or time to Z domain. Then from Z domain you can go to digital frequencies and all that. So it is unlike, because it does not transform the signal from one domain to another, but it actually transforms the signal, but it does not have a domain transformation. This is the difference. And so it is not that type of transform, but it's still a transform. All right. Yes. And in the previous transform, Z and all that, Z transform and S transform and Fourier transform, the signal in both the transform is the same. You just represent the signal in time domain, or you can represent the same signal with respect to, Fourier transform or Fourier series in frequency domain, right? Signal is same, but its representation is in different domains. But here, once you pass the signal through a Hilbert transform, the signal itself changes. All right. Now, how is this possible? How do you change the signal? So let us say I have a signal x of t and I want to take its transform. This transform becomes x hat of t. So how this is possible? I will just delay all the frequency components of x of t by a phase of 90 degrees. This is what I have done. So I have to make a phase change, a phase delay of 90 degrees. If I'm able to do that, the new signal will be the Hilbert transform of the original x of t. This means that x of hat t will have the same frequency components as present in x of t. Okay? Even their amplitudes will remain the same. The only change will be the phase delay. You will just delay the signal by 90 degrees. So for example, if I have x of t this, cosine this, I just delay it by minus 90. And if you delay the cosine by 90 degrees, cosine's peak value is at 0. If you delay by 90, the peak value comes at 90 and that becomes a sine. So this signal will become a sine. So Hilbert of a cosine is actually a sinusoid. Alright. A delay of pi by 2, ये ना थोड़ा गलती, ये at लिखा हुआ है, t इसके साथ मिला लें. Alright. So a delay of pi by 2 at all frequencies means that ej2 pi ft will become ej2 pi ft. अच्छा, there is also an error here. This should be a bracket. ये ना मेरे नोट्स पे आ रहे हैं, इसकी थोड़ी थोड़ी गलती, वैसे इसने सही लिखा है, बस वो आपको पता है, जो आप बुक्स भी छापते हैं तो प्रूफ रीडिंग नहीं होती है और फिर उससे गलतियाँ हो जाती हैं. जितनी मर्जी आप कोशिश, गलतियाँ फिर भी हो जाती हैं. Alright, so what is delay of pi by 2? So this is, let us say this is my frequency. Alright, I'm deliberately writing this ej2 pi ft so you can very well see that what is the change in the Fourier transform. What is Fourier transform? Fourier transform actually represents your signals in terms of ej2 pi ft's. All right. So that is why I have done this. Okay, this eigenfunction. So I just put a delay of minus pi by 2. All right, in radians to my original signal. So I can write this as ej2 pi ft minus pi by 2. So become ej2 pi ft, this becomes e minus j pi by 2, cos of pi by 2, sin pi by 2, cos pi by 2 goes 0, minus j sin pi by 2 becomes, sin pi by 2 is 1, this becomes minus j. So a delay of pi by 2 resulted that the frequency components are being multiplied by minus j. Similarly for negative frequencies, e minus j2 pi ft, what will be the meaning of delay? We all know that meaning of delay, for positive it is minus, but for negative it is plus. ठीक है, या आप इस तरह से देख लें कि हाँ जी इसके अंदर माइनस किया, जब आप बाहर से करेंगे तो ये प्लस हो जाएगा. So we all know for negative delay has opposite sign. It is not minus, it is plus. Alright. So e plus j pi by 2 is j. Alright. So we could see that in negative frequencies we are just multiplying by plus j. So this is what is saying that positive frequencies you are multiplying by minus j, negative frequencies you are multiplying the spectrum by plus j, and this is what is Hilbert transform. So Hilbert transform transforms xt to x hat of t, but in frequency domain what it does, it just multiplies the Fourier of x of t by signum of f. This is sine of f. So for positive frequency this will be plus 1, for negative frequencies this will be negative 1. So for positive frequencies will be positive 1. So you will have minus j. This is what we were saying, that for positive frequencies we are multiplying the spectrum by minus j. If you have negative frequency, sine of negative will be negative, negative becomes positive. You are just multiplying the spectrum by positive j. Alright, for negative frequencies. This is what is the Hilbert transform doing. Alright. So signum of t. Achha, we also know that what is the Fourier of sine of t. So sine of t Fourier is given as follows. You can see also in the previous chapter it is given. So I applied the famous duality. So you know this comes here and this goes here. So this minus sign come here, can come here. Both are correct, and we have also seen in the last chapters. So I put a minus here uh, because this minus here, and then I can take this minus j here. So this will become 1 over pi t is a Fourier inverse of minus j signum of f. So I was multiplying my input signal by this in the frequency domain. This means in the time domain I will be convolving x of t by the inverse Fourier of minus j signum of ff, which is 1 over pi t. So x hat of t can be obtained by taking the convolution of the input signal with 1 over pi t. Alright. So we can now have understood a little bit basics of क्या कहते हैं Hilbert transform. So now let us go to this proof. We've done all of this. Yes. So, alright, we have understood what is a Hilbert transform. It means you pass your signal through this impulse response, or in other words, you multiply your spectrum by HFF. And what is HFF? HFF is just for positive frequency it is minus j multiplied by minus j. You know, for output will be HFF into XFF. So for positive you will just multiply by minus j, and for negative you will just multiply by j, or the thing which I told you, it will be minus j sine of f, which will just actually give you these things. Acha. Acha. Now we need to know this proof. All right. So the proof is given in the appendix, but again I found that many steps were missing, and they might cause confusion because remember many end problems as well as problem the quiz, they come from this double and sideband mix up, and so you need to be well versed in its mathematics and also the understanding. So I will try to make this clear. I will also use my notes wherever there is deficiency in the book or some error. All right, so let us say MT is my signal, its Fourier is M of f, and I want just the upper sideband. All right, I just want the upper signal sideband of my AM signal. For that, I want to eliminate my lower sideband. So first of all, I make my क्या कहते हैं उसको double sideband signal. And how can I eliminate? So one way of elimination was that you pass it through a high pass filter. So high pass filter will just pass above FC, so you will just get the upper sideband. All right. So I know that those filters are very hard to implement, but mathematically this is what is required. So I will try to make a signal system or signal processing approach to generate my single sideband for upper single sideband signal. So I need to multiply my double side signal by this filter. Okay, and once I will multiply, all right, so I will in frequency domain I need to multiply the Fourier of my signal with the frequencies or the Fourier of the filter response. So for an LTI system, if you have a signal, it passes through a filter. The output we all know is convolution in time, and in frequency it is just the multiplication of the input signal Fourier with the filter response Fourier or frequency transform. All right. So now what is the Fourier of my filter? So here I use my notes again. So I'm sorry, just a little bit, the picture is not that sharp. It is blurred, but I think cam scanner couldn't take the proper picture. But again, you can just see. So this is my double sideband signal. I apply a filter with this response, so that I can just cut off the upper sideband, and I will get the upper sideband. This lower sideband will be neglected, deleted, or zeroed out once I pass it through my this type of high pass filter response. So, but I'm not actually passing it. I'm just discussing this with respect to signal systems approach. So remember that for a communication engineer, he has to have both sides of the coin. Okay, one side is signal systems approach. Okay, and the other side is electronics approach. Okay? So he has to switch between these two sides. Many solutions are found by our communication engineers with respect to signal system approach. ठीक है, and many industrial uh, examples are there, ठीक है, and uh, but many a times you have to go to electronics, ठीक है. So now I have my double sideband signal. I will just multiply my double sideband signal with this high pass filter. I will get my upper sideband, this upper single sideband AM signal by just multiplication. All right. Now, so this was, the book uses unit step. This is less simple. No, we used to use UF minus FC. All right, U of F, unit step from 0 to, unit step starting from 0 going for positive frequencies. So this will be UF minus FC. So this unit step has shifted to FC. But book uses the notation of -1 for unit step. So I don't want students to get confused. That is why I've just put U minus 1. So in exam, there's no problem. You can use the old notation of UF minus FC. All right, UF minus FC, this will be multiplied with this spectrum. Now, what was this? This spectrum was MF minus FC. So you can see here that its Fourier will be MF because of this multiplication, MF minus FC, and so this will be MF minus FC, and this will be MF plus FC because of cosine. We know cosine is a 1/2. That is why here derivative multiplied by 2, so 2 cancels. So you will have the spectrum as ACMF minus FC at FC and ACMF plus FC at negative FC. All right, this is the spectrum. So I just multiply the spectrum by my high pass filter. So this will be the positive frequencies multiplication, and for the negative frequencies this will be F plus FC. MF plus FC will be this spectrum multiplied by, ये पता नहीं क्यों कट गया वैसे, इसमें तो क्लियर लिखा था. This will be minus F. Remember what is minus F? Minus F means unit step is going from 0 to negative frequencies. But if I want to shift my unit step from 0 to FC, I have to not plus, I have to minus. All right. So I have to do minus F minus FC, and in my flipped unit step will now be shifted to minus FC. All right. So this will be my segment. This is actually minus FC. It's not clear, but it is minus FC. Now we also know from our previous Fourier transforms that if I have a signal M of F, it is being multiplied with a unit step function, its Fourier inverse will be M of t convolved with Fourier inverse of this unit step. And I also know that if I shift both of them at minus FC, all right, this will correspond to my original signal. This was being multiplied by a high frequency exponential EJ2 pi FCD. अब बाजी को उठा दें मुझे, अच्छा देखना अच्छा किसी घंटी पे जा देगा. I'm sorry for this interruption. You are teaching from home, so you have these interruptions. So I will try to come back to this lecture. अच्छा हम क्या कह रहे थे? All right. So you multiply this with high frequency carrier. This means you are shifting your spectrum to these two. So you have actually got this thing. So you have actually got, uh, the time domain, representation of this part. Now for this part, and the book has used a very unusual way of explaining this, and I have some, mathematical differences the way the book has done this. So I'm not clear. So it is what much easier that the book could have used basic, signal processing tools, which I am doing in front of you. That is why I have done it in my notes. So again, we if I have my m of f, and it is being multiplied with u of minus f, so I know its time domain will be m of t convolved with Fourier inverse of u minus 1 of minus f. All right. Now I will take this to higher frequency but negative frequency. So what I do, I advance my signal plus fc, but this is, f. I advance is very good plus fc because it was positive f, but this is minus f. Advance means I have to do minus fc. In other words, if you don't, if you got confused, always take this minus outside. This will be f plus fc. You're actually doing f plus fc but with negative sign. That is why it becomes minus f minus fc. So its Fourier inverse will be what? It will be, Fourier inverse of the original shifted by a high frequency carried with the negative sign. So e minus j2 pi fct, right, will be the Fourier inverse of this thing. So if I say that my single sideband upper single sideband signal has a time domain representation as u of t. So what will be my u of t? U of t will be just AC, and all that frequency will now be represented in the time domain as follows, as we have just seen above. And similarly here again AC, and all the negative part will be represented by this empty. ये जगह नहीं थी यहाँ पे, so empty convolved with all of this thing. ठीक, जैसे इधर था वैसे इधर भी आ जाएगा. इसके बाद ये एरो था, एरो के बाद ये this comes here. So I will get this as my time domain representation of my upper single sideband signal. Now what is this u of f? So first of all, what is this unit step function? I can always write my unit step function as 1 plus signum of t or sine of t, because for positive frequency sine of t is plus 1, 1 plus 1 is 2, 2 divided by 2 is 1, so you're getting a 1 for unit step. For negative, this is sine of 1 is minus 1, 1 minus 1 is 0, so you get a 0. So unit step is from 0 to 1 as you go from negative to positive time. Now, and also know the signum of t has this Fourier 1 over j pi f, sine of t has this Fourier. So half plus half of sine of t will have a Fourier of half. One's Fourier is DC signal, its Fourier is delta of f, and sine of t is this. So this is this. It's a Fourier of u of t will be this, and I apply the famous duality. So this u of t becomes u of f, putting minus t because of book notation, and this will totally become t. I can put negative here or here, it is my choice. Okay, so I put negative first of all here. So we delta minus t, this will be minus 1, and delta t is it says add 0 minus plus, it doesn't make an effect, this becomes delta of t, and this j comes in the numerator, this becomes minus, you multiply by j and j, this j square, j here, j square is minus 1 cancels as you have positive j in the numerator, and so your Fourier inverse of this thing u of f is equal to this thing. Similarly, your Fourier inverse of u of minus f, you can directly see from here u of minus f. So you put a negative here, these two will be positive, and when this j go above, this will be minus negative. Or you can go from here to here. So you put minus f here. Wherever you have t, you have to put a minus t here. So you will get the same expression here or here. Again, delta t is symmetric, so you can write it like this. So we have now the Fourier inverse of u of f as well as u of minus ff. Put their Fouriers in this equation. Found the Fourier inverses of these two. I will put their Fourier inverses in equation 4. So I will be getting their Fouriers here and their Fouriers here. Their inverse Fouriers will be here. Now when m of t is convolved with a delta t function, you get the m of t, very famous shifting theorem from your previous courses. M of t convolved with j02 is constant. M of t convolved with 1 over pi t is a Hilbert transform m hat of t. Rest is same. Same thing happens here. M of t, this will be minus j m hat of t. Now what you do, you can open your EJ by the Euler's identity. This EJ is also opened by the Euler's identity. Alright. And now you can do the relevant mathematics. You will have 8 different products, and these are 8 different products that you will be getting. You can see this will go with this, and this will be added. This will go with this, and minus plus this will be subtracted, and this will be nullified or cancelled out. This will also be cancelled out, and this will be added. This is also minus, j square is also minus. So you will get this. All right, and you can do also had this 1 over 2, so this 1 over 2 will cancel with this 2, and hence you will get the upper side band signal as minus. And you can see in the book he has also given a very good, so this is, so I just copied from the book but explains some stuff which were confusing in the book. This was the upper side band. You can also get the lower side band with the plus sign by this formula. Upper and lower is equal to UA double side band. You put the value of the upper plus the lower, so lower will be the double side band minus the upper, and you will see the lower side band will come out to be with a plus sign. So negative or plus, you can get any of the single side bands of your double side band signal. So without doing any filtering, you just take the relevant Hilbert transform and you will get the single side band signal. If any questions you can ask. I will take your attendance also right now by the help of Alright, this has been downloaded. Now coming back to the lecture, we still have 2 minutes. ये तो हो गया, ठीक है. So we have got this signal. So coming back to here, so we have, now let us see some examples. So this is this signal. So he says, all right, fine, it's upper and lower sideband, single sideband signals, or we say, all right. First of all, m of t. First of all, I find it's m hat of t. M hat of t for cos is always a sine. So I write my upper and lower sideband signals from the previous proof. Will be m of t, m hat of t, m of t, m hat of t. So So just put mt and this is m hat. Cos remains the same. Just put m and m hat. So cos sign remains same. This is my mt, this is my m hat t plus negative. This will be upper and lower side band. So for if I put negative, this will be double cos sin. This is cos alpha plus beta. All right. And for negative, this cos minus beta, cos alpha minus. This is cos alpha minus. So you get the upper side band and the lower side band signal. And these were the same signal. In the previous example, we also saw this was a representation for the upper and lower side band, but now we are being able to separate the upper from the lower and the lower from the upper, or both of them have been extracted from the double side band signal. All right, the time is up. If still you have any questions, you can ask. All right, so no one has any question. I will end the recording as well as the lecture.